During lesson 111, you were introduced to the first type of physical quantities, known as the fundamental or basic and derived quantities. In lesson 112, you were also introduced to the second type of physical quantities, described as the dimensional and dimensionless physical quantities. During this third lesson, 113, you will learn about the third type of physical quantities known as the scalar and vector quantities. What are scalar quantities and what are vector quantities? How are the scalar and vector quantities represented on papers? And how do we operate scalar and vector quantities? Scalar quantities. What is a scalar quantity? A scalar quantity is a physical quantity that is completely described by its magnitude, that is the size, and its unit only for it to make sense. Examples are area, length, volume, density, speed, energy, mass, and time. Scalar quantities are usually represented by the small characters of the English alphabets. Time, for example, is denoted by the small letter T, while mass is represented by letter M. The length of an object is represented by letter L. Scalar operations. Scalar quantities can be operated upon by using the ordinary arithmetical processes of addition, subtraction, multiplication, and division. Vector quantities. A vector quantity is a physical quantity that requires magnitude, that is a size, unit, and which also depends on a given direction for it to be described fully and for it to make sense. Examples are displacement, which is written as 300 kilometers 50 degrees east, or force F, which can be written as 400 newtons 90 degrees east. Momentum P can be described as 500 kilograms per meter second to the right or to the left. Velocity V is written as 90 km per hour north 70 degrees east. How do we represent vector quantities? Vector representation. In most textbooks, vectors are usually represented by the bold, higher characters of the English alphabets, such as A, or by a small letter with a small arrow on top of it. Geometrically, a vector quantity A can be represented by a line segment with an arrow head, as shown in figure 131. Magnitude of a vector. The magnitude, that is, the value of a vector A, is denoted as A, that being bold, or just letter A. We talk of absolute value of a vector to mean the magnitude of the vector quantity. Distance and displacement distinguished. Moving through a curve ACB is the same as moving through the straight line AB. as shown in figure 132. Moving through the curve ACB describes the concept of distance, while moving through the straight line segment AB describes the concept of displacement, as shown in figure 132. In figure 133, AC, CB, or AD and DB are also displacements, while AB is described as the resultant displacement. That is, AB is equal to AC plus CB, or AB is equal to AD plus DB. AB is the summation of the two displacements. Resultant displacement. In figure 133, if an object has a displacement AC followed by another vertical displacement CB, or if it moves from A with the vertical displacement AD followed by a horizontal displacement DB, the straight line segment AB describes what is known as the resultant displacement of the two displacements. Consider the movement of another object in figure 134. Moving through the curve PRQ as a distance, which is the same thing as having a displacement PQ. If the object now moves back from Q to P through S, the subject will be observed to have moved through a distance of QSP and a displacement of QP, which is equal and opposite to displacement PQ. The displacement of the object P to Q and from Q to P is 0. This is because PQ is equal to minus QB. Therefore, PQ and plus QP is equal to 0. Consequently, the total displacement is 0, but the total distance is PQR plus QSP. Further information about vectors. A, equal and opposite vectors. A vector A having direction opposite to vector A but with the same length is denoted as minus A. That is, vector minus A is equal and opposite to vector A, as shown in figure 135. Null vector. When equal and opposite vectors F1 and F2 are applied to a point O, as shown in figure 136, what will be the resultant, therefore, effect of the two forces at point O? The situation can be likened to the tug-of-war game, where two teams, A and B, pull on a rope to determine the stronger team with reference to figure 137. If team A pulls towards the right of point A with F1 and team B pulls towards the left of point A with force F2, the umpire of the game stands at point O to determine the winner. If the reference point O shifts to the right, this means team A wins the game because F1 is greater than F2. On the other hand, the reference point O, if on the other hand, the reference point O moves to the left, it means B wins the game because F2, in this case, is greater than F1. However, if reference point O remains at the same point for a given time interval as decided by the umpire, then it can be concluded that F1 is equal to F2. That is, F1 minus F2 is equal to n, which is equal to 0, where n, the first n, is described as the null vector, which is equal to a 0 vector. Note that you cannot define the direction of a 0 vector. Such a vector is described as a null vector or zero force, as shown in figure 137. By definition, therefore, a null vector is a vector whose magnitude is 0 and whose direction is not defined. A null vector is always obtained when we multiply a vector by a 0 vector. Equal vectors. Two vectors A and B are equal if they have the same magnitude, that is size, and direction, regardless of their initial and final points. They will be parallel and they will be in the same direction as shown in figure 138. The two vectors are therefore equal if they have the same magnitude and direction, no matter where they are in space. Vector operations. Vector operations do not follow the same arithmetical processes as in the case of vector addition, vector subtraction, and vector multiplications. Example 1. The displacement of a body from point A to point B is 4 kilometers east. If it is followed by another displacement from point B to point C with 3.0 kilometers east, the resultant of its movement or displacement from A to C is 7 kilometers east, as shown in figure 139. The resultant displacement is therefore written as AC is equal to AB plus BC, which is equal to 7 kilometers east. Note the magnitude, the unit, and the direction east. Example 2. In another situation, if the object is given a displacement from A to B as 4.0 kilometers east and from B to C as 3.0 kilometers west, as shown in figure 1310, the resultant displacement is AC, which is 1.0 kilometers east. That is, AC is equal to AB plus bracket minus BC. That is, notice the minus as being the opposite direction. Hence, AC is equal to 4 kilometers east minus 3.0 kilometers west, which will now boil down to 1 kilometer east, as shown in the diagram. Again, if the object moves from A to point C with a displacement of 3 kilometers east and then moves from C to point P with 4 kilometers north, as shown in figure 1311, AB is the effective displacement, but the sum is not the same as an arithmetical sum. Vectorially, AB is equal to AC plus CB, but the size of AB is not 7 kilometers, and the direction theta must be determined so that AB can be expressed as a vector, magnitude, unit, and direction. In summary, this lesson has been focused on the concept of scalar and vector quantities as the third way of categorizing physical quantities. Scalar quantities are those physical quantities that can be expressed in magnitude and units only for them to make sense. They are usually represented by the small characters of the English alphabet. Scalar quantities can be operated upon by using the ordinary arithmetical processes of addition, subtraction, multiplication, and division. Examples of scalar quantities have been given in the text. Vector quantities are the physical quantities that have magnitudes, units, and directions for them to make sense. Vector quantities are usually expressed by the bold high character of the English alphabet in most textbooks. Small and bold characters of the English alphabet are also used. Vector quantities are geometrically represented by a line segment with an arrow on the line segment. Examples of vector quantities have been given in the text. It is important for you to know that the element of direction shows the basic difference between scalar and vector quantities. For example, the difference between distance and displacement is vested in the use of direction to make sense. The following concepts have also been explained to further describe the examples of vectors as equal and opposite vectors, null vectors, and equal vectors. Vector quantities do not follow the ordinary arithmetical processes such as the vector addition, vector subtraction, and vector difference, and vector multiplications. We employ Pythagoras theorem and trigonometrical ratios in vector operations. Cosine and sine rules are also used to determine the magnitude of resultant vectors. Thank you. See you in the next lesson.